In this lecture, I'm going to kind of springboard off of Dan's introduction and spend some time talking about three topics that I think economists may find particularly interesting and where I think economists have some potential to make contributions to research that would be complementary to the statisticians and computer scientists who've been working on these sorts of problems. And so in particular, I'm going to talk about three different things. I'm going to think about the problem that statistical agencies and other data custodians face when they're trying to trade off privacy protection versus data accuracy. And differential privacy, as Danny got into, provides some tools to help clarify how we think about balancing these two objectives. I'm going to argue that kind of the decision about where we land is fundamentally an economic problem. And then I'm going to turn to thinking a little bit more systematically about how differentially private data allow us to be more careful when we think about learning from privacy protected data. So as social scientists, we know that we need to be careful to take account of the fact that the thing that we're interested in learning about is not always necessarily the thing that's being measured in the data. And differential privacy gives us a system for doing sort of privacy aware analysis when we're engaged in research. And then finally, I'm going to talk a little bit about the concept of accuracy. We'll talk a lot about trading off privacy and data accuracy, but whereas the concept that we get from differential privacy of a notion of privacy loss is extremely specific and very precise, the notion that we get of accuracy is not so clear. And so I'm going to discuss accuracy in terms of improved decision making towards the end of the talk. Okay, so let's get right into the first thing. So statistical agencies face this sort of dual mandate where they have collected some information we're going to think of as being confidential, and then they're charged with producing accurate statistical summaries that can be made available to the public for all kinds of decision-making purposes. But at the same time, they're responsible for maintaining the privacy, the sensitive characteristics for the individuals and businesses that have entrusted them with their information. And so what we get from differential privacy is a very specific concept of what privacy loss means. And it allows us to make this concept of a trade-off between privacy and accuracy very clear. So we know from various theorems that each calculation that's based on the data is going to consume some part of the privacy budget. So Dan alluded to this, and I think he's going to discuss composition more in a later talk, but essentially, say if we're going into the current population survey, ignoring issues of sampling for the moment, say we want to know the number of unemployed individuals, and we're going to publish that, say, using the Laplace mechanism with parameter epsilon1, and that gives us a total privacy loss of epsilon1. Then we go back and we want to calculate, say, the number of labor force participants. Well, they're going to be the same individuals, so now we've incurred a second privacy loss of epsilon2, and so on. So the total privacy loss kind of accumulates in this additive fashion across all the different statistics. And so we can either think of this as sort of the total cost of producing the statistics that we're interested in, or we could think about it sort of in reverse, that we may have a sort of total privacy budget, and then we have to sort of figure out how we want to allocate, say, that epsilon total across all of the different statistics that we're interested in. And so what that means then is that, say, if we want to obtain an estimate of the employment count that's more precise, then we're going to have to sacrifice precision somewhere else. And these are not any more abstract decisions. The Census Bureau is making decisions about where to set this privacy loss budget on different products with increasing regularity as it shifts to thinking about formal privacy as a default mode of protection. And so I've just listed here a few of the different settings of epsilon for some products that we'll talk about later on today. So in my 2019 AER paper with John Aboud, we kind of argued for taking an economic perspective to this question of where to set epsilon. So we know that we can think of the data publication problem as having two parts. There's a production function So differential privacy essentially gives us a production technology. And that production technology tells us how we can convert information in the database into statistics that have a given level of accuracy. So kind of returning to this earlier example, if we think about, if we want to publish, say, the unemployment count, and we want to entail no privacy loss, then we would be setting the variance, say, of that Laplace noise to infinity, and essentially it would be just as good as not publishing anything. We might as well have not even bothered. Conversely, if we wanted to incur sort of infinite privacy loss, we were willing to tolerate that, then we're adding Laplace noise that has no variance, and so then we might as well just be publishing the sensitive data in the first place. So this is our production technology. This gives us a locus of points, right? There are points available in between that describe the different combinations of privacy loss and accuracy that are feasible. And so we really have sort of a finite resource. It's this information in an existing database, and we can allocate it in between generating statistics that we can use for calculations that have increasing accuracy, or we can reserve some of it to protect against privacy loss. And the key idea that comes from economics is, so we know this is fundamentally a social question, and what economic analysis tells us is that an optimal allocation should equate the marginal rate of transformation, that is, how much it costs to increase statistical accuracy or increase accuracy in decision making, measured in units of increased privacy loss. And we know that optimally we want to equate that to the willingness to pay for increased statistical accuracy in terms of foregone privacy loss. And so from the differential privacy side, from the computer science side, we get a good notion of what this production technology looks like, but we do not have a very good notion of what these social preferences look like, or what the social welfare function would look like if we tried to account for the value of statistical accuracy and the value of data privacy. And so where more theoretical and empirical research is needed is in coming up with better ideas to think about how we understand or conceptualize the value of obtaining more statistics or of obtaining more accurate statistics. For instance, how much would we be willing to pay right now to have more accurate information about, say, the prevalence of COVID-19 cases in a local jurisdiction? Or how much would we value having had somewhat more accurate statistics from the current population survey during the pandemic and lockdowns? Those are questions that we can pose precisely, but we don't have clear answers to them. We don't also have clear answers to understanding the costs of incremental privacy loss when we measure privacy loss using the concept of epsilon that we get from differential privacy. This idea of sort of bounding a Bayes factor on posterior inferences. What's the actual cost associated with incrementing that privacy loss? So these are questions where research is ongoing, but I think more economists have a lot potentially to contribute. Okay, so moving on, second topic I want to think about is the challenge of learning from privacy protected data. And in this context, I sort of want to focus on what I think is a false dichotomy. Some people that's out there, that the data that we're currently using are not subject to any privacy protection. But when I get into it, so I want to develop a concept of a privacy aware analysis. And this has come up in some of the previous talks. And so I'm going to work through a very general model just to sort of fix ideas, just to fix ideas. So the idea here is that we can think about the statistical agency as having data that come from some population and is in possession of a complete data matrix. So we'll ignore for the moment questions of sampling and missing data. So the statistical agency is in possession of the complete data matrix D. And as researchers, we might think that there is some data generating process which we could specify in terms of a data model parameterized by this thing we call the process parameter theta p. And we might have a prior over that. And so in general, there are two estimands of interest. One would be functions of the data themselves. These would be finite population estimands. So that would be something like, we need to know the total number of individuals in each state for the purposes of congressional apportionment. But we might also be interested in learning functions of the superpopulation, so functions of the process parameter. So the idea that I want to develop is sort of with analogy to the idea of ignorable missing data. We could also have the concept of ignorable privacy protection. So the data that we observe are not the data D that were collected. The data that we observe are data Z, the data that were published. And this is the case whether or not we're thinking about a system that has been operated using differential privacy, or indeed the types of privacy protections that are currently being used at the Census Bureau and other statistical agencies. The data that we get out as researchers are not the same as the data that went in. And regardless, the data were subjected to some kind of privacy model, which we could think of as being probabilistic or deterministic, where the probability of observing the published data depends on the input data and some parameter that describes the privacy model. So in the randomized response application, for instance, theta m would be p, the probability that the respondent is told to lie, or the probability on the spinner. And that parameter we could think of as also having a prior. And if we have all of this machinery, then kind of in the most general case, we know what the likelihood is for the published data. We could obtain it by integrating out the true data from the product of the privacy model and the data generating model. So in that case, we would be doing inference on the posterior distribution of the process parameter given the published data, which again, we could obtain by just integrating over the posterior distribution for the process parameter given the true data, and the posterior predictive distribution for the true data given the given the published data. And so we can characterize ignorable privacy protection here as just saying that privacy protection is ignorable in exactly the case where the posterior distribution for the process parameter given the published data is exactly equal to the posterior distribution for the process parameter given the true data, when the true data happen to be equal to the published data. Or in more simple terms, basically privacy protection is ignorable if we can just plug the published data into the true data estimator and everything will work just fine. If that's the case, then we'll say that privacy protection is ignorable. And so this leads us to three questions we should be asking about any privacy protection system. First, is it ignorable? Second, if it's not, can a privacy-aware analysis be conducted based on what we know? And this means that we're going to have some information about the protection model, about the privacy model. And if we don't have any information about the privacy model, is there some way to discover that information, to back it out from things that we know in the data? So to kind of bring this a little bit down to earth, the first privacy protection method we can think about is top coding. So top coding in the current population survey says that if your household income is 200,000 or above, it's going to be suppressed so that we don't give away too much sensitive information about households. In the current population survey in 2017, that threshold, there were between 7 and 8% of households were above the threshold. So this form of statistical disclosure limitation, researchers are used to thinking about it. This is the kind of intuitive thinking about privacy protection we engage in all the time. But we know that this kind of privacy protection is ignorable if the inferences that we're interested in, say, are quantiles less than that fall below the top code. So we know that we can estimate 90-10 earnings ratios or income ratios in the current population survey. But of course, it's not ignorable if we're interested in quantiles above the threshold. And occasionally, if we have some additional information about the distribution of incomes above the threshold, then we could engage in a privacy-aware analysis. But there are other sort of more insidious forms of privacy protection that are currently in place that are not formally private. So for instance, the suppress and impute says if there's a value of a sensitive characteristic, say it's age at 50, then I'm going to suppress that value. I'm going to use some imputation model and replace that value with an imputed value, say 51. What we know about missing data imputation in general from a paper by Chris Bollinger and Barry Hirsch in the Journal of Labor Economics is that it's non-ignorable in most cases. If the imputation model is less rich in a sense that they make quite precise than the model that you're trying to estimate, then the use of the imputed values is going to induce bias. And of course, for missing data imputation, you can you can throw out the imputed values because they're flagged in the data, but when suppression and imputation is used for privacy protection, the values aren't flagged. And so in this case, the privacy model is non-ignorable, and it's not possible to engage in a privacy-aware analysis because we don't know the rate at which suppression is being carried out. We don't know the model that's actually being used to impute the values. And in fact, we don't even know what the variables are that are being imputed. And so it's also not possible to discover what this is and try to adjust inference for it. Swapping is a similar story. So swapping is another method that also tries to protect sensitive characteristics, essentially operating in the following way. So if there's a record that's deemed to be high risk, say an individual who lives in, say, Athens, Georgia, who has a particularly large family and or a high income, then you could take, you can swap that record on the basis of some matching characteristics to a nearby jurisdiction where that individual is not such an outlier. So you're essentially trying to move outliers into areas where they're not outliers. So this has the advantage that it preserves counts on key characteristics, and so it allows enumerations to remain, on particular characteristics to remain fixed. And it can help with preventing the disclosure of sensitive attributes. But it's ignorable only in the case that you only care about the matching variables. It's not going to be ignorable. In fact, it's going to just destroy the covariance between any of the matching and the other variables. And once again, the parameters of this process are secret. In fact, they're kept secret deliberately because it's believed that publishing information about these parameters would allow attackers to undo the privacy protection that's built in. So this is unlike formal privacy models where the whole point is that the methods can be made transparent, which then facilitates privacy-aware analysis. So these distortions might matter a lot, but we don't actually know because we don't know anything about the model. We don't know too much about the error that they introduce into the data. So there's a fairly interesting analysis in a paper by Alexander, Davern, and Stevenson, where they compare population estimates from the 2000 census, the tables that are based on the 100% enumeration, with tables that they generate themselves from the 5% public use microdata sample. And they're looking at population estimates disaggregated by age and gender. And so the way that these protection mechanisms work, they should be implemented the same way on the data that are used to generate the 100% tables as on the public use microdata sample. And so that means that up to sampling error, the estimates from the public use microdata sample and the published tabulation should agree. And so that's the case for men and women whose ages fall below about 64. The two estimates line up. And where they start to separate is around age 65, say in the 5% microdata sample. For men, we see that there are too many men close to age 65 in the public use microdata sample relative to the 100% tabulations. And then again, and too few men between ages sort of 67 and 80. And so it's not entirely clear what's happened here other than that we know that this is due, according to some technical notes, this is due to some kind of misapplication of privacy protection mechanisms in one or both of these sources. And so it looks like, at least potentially, that the distortions introduced by privacy protection methods could be ignorable if what you're interested in is prime working age individuals, and perhaps not ignorable at all, and in fact quite destructive if you're interested in individuals above age 65. But of course, if they hadn't made this error, we would never know even that much in the first place. So this is not exactly telling us entirely what's going on, but it suggests that these distortions could matter quite a bit. Final form of traditional privacy protection I'll discuss is self-suppression. Self-suppression, I think most economic researchers will be familiar with, but the idea is that, especially in business data, we could have cells, if we're looking, say, at a very narrow county and industry, we might have a cell where one large firm dominates. And so by looking at the tabulated data, you might be able to infer something like the total receipts or the employment, trade secrets of that firm. So the Census Bureau is committed to protecting those firms against that sort of disclosure. And so the method is to just blank out cells where you think that that might be particularly disclosive. But because tabular data have the property that they sort of need to sum up to margins, then that means that you can't just blank out the cells that you're worried about, because you can just do some subtraction and figure out what the suppressed value was. So then you've got to blank out some more cells to prevent these sorts of subtraction attacks. And then you might have to blank out some more cells to prevent subtraction attacks on those, and so on. So you end up putting increasing number of holes in your data. So this is a protection method that's used in tabulations from the economic census and have been used in the county business patterns. So self-suppression is not going to be ignorable unless the suppression was random with respect to your estimand of interest. But since it's explicitly a function of sort of how dominant firms are relative to the data, it seems like there are many cases where that's probably not going to hold. So if it's not ignorable, then what can you do? Can you engage in a privacy-aware analysis? In general, we don't know exactly what the suppression rule is. But there's another thing you can do. You can try to hack the protection. So there's a very interesting paper in the 2020 NBER working paper by Eckert, Fort, Schott, and Yang, where essentially what they do is use sort of commercial grade linear solvers to take all of the restrictions that are implied in the county business patterns and use that information to sort of try to reverse engineer what the suppressed values in the county business patterns were. And so I think this is a very interesting approach, and I'm very curious about exactly how effective it is. I don't actually know, but one suspects that it could be. But what's interesting to observe about this is now we have a situation where the researchers kind of pursuing their interest in getting more accurate statistics are actively trying to undo the protections that are being built into the data by the data custodians. And this seems to me to be a situation that is sort of undesirable, when we could replace this with a system where we could offer the same degree of protection to the firms contributing their data, and allow researchers to have as much information as they need to make adjustments for the privacy protection, and to not be able to undo the privacy protection. We know that suppression is not ignorable. So in a paper that I'll talk about a little bit more in my second talk, Chetty and Friedman introduce a method of privacy protection that they used to publish a data set called the Opportunity Atlas. And they were quick to point out that if instead of using the formal privacy model that they set up, they had instead used a count suppression rule, that it would in fact destroy inferences on certain questions that might be of interest to social science researchers. So they focus on the example of looking at the relationship between the single parent share in a tract and the teenage birth rate for Black women raised in low-income families. And it turns out that the cell suppression rule, which suppresses cells that have a small number of individuals, is correlated with the single parent share and with the teenage birth rate in a way that alters the estimated relationship between these two. And again, the point is, with the count suppressed data, it would be very difficult to conduct a privacy aware analysis that would allow you to draw the inference that you would get from the noise infused data. So we know that analysis needs to account for both the phenomenon that we're interested in, but also the way that that phenomenon is being measured and reported to us. But accounting for traditional privacy models either can't be done or, in kind of extreme cases, actively undoes the privacy protection that we were trying to achieve in the first place. And so what that means is that privacy-aware analysis requires more transparent formal privacy systems. And this is one of the key advantages of working with a differential privacy model, is that we can know exactly the process by which the data were processed. And then if we kind of hold to Danny Goroff's idea that if you can't deal with the distortions that come from a known distribution, we're going to take away your social science card. Maybe that's a little harsh, but probably not. Okay, the last thing I want to focus on is trying to understand what exactly it is we're discussing when we're talking about accuracy. So in other words, when you draw this sort of diagram, we know that the horizontal axis is this measure epsilon that tells us about sort of the maximum increase in the Bayes factor for some adversary, how much an outsider can learn or increase their posterior odds about, say, some sensitive characteristic. The concept of accuracy is not so clearly defined. And it's important for us to think about what it is, so especially if we're interested in being able to calculate sort of optimal privacy loss. So I want to think now about kind of accuracy as it applies to decision making. So in general, what we're trying to do with data is not just publish statistics, but we're trying to make decisions on the basis of those data. So again, if we think that D is a population level data set, Q of D is some population statistic that we're interested in, and now A is our published output, well, accuracy is always going to be based on some kind of concept of a loss function. So the question is, how are we going to define that loss function? And so we could think about it in terms of the different types of decisions we might need to make. So in social science research, we might be either trying to learn the parameters of some model or engage in hypothesis testing, which essentially amounts to a decision problem. But the data are also going to be used to make public policy decisions or used by businesses to make business decisions, say about where to locate a firm. And the question is whether or not those different use cases require different concepts of accuracy. And if they do require different concepts of accuracy, how would we balance them off when we're trying to, again, make these decisions about where to set the privacy loss budget? It also applies to what kinds of mechanisms we plan to use. So this problem is hitting the Census Bureau hard at the moment. This is a list of proposed accuracy measures that I got from a Census Bureau document published in March. And this is the list of different accuracy measures that they're using to determine whether or not the 2020 disclosure avoidance system, which is using differential privacy, is going to be fit for various use cases. And so in that document, they had described, say, 6 different categories of use cases, say where you're allocating something, some resource, but there's sort of a zero-sum total, or you're trying to think about allocating some total across different categories. You need to know information that's precise about a single year of age, and so on. Each of those different use cases may be more or less well represented by different types of accuracy measures. And so we've got kind of an increasing kitchen sink of different concepts of accuracy that are being used to evaluate this disclosure avoidance system. So the mean or median absolute error, the mean or median numeric error, the root mean squared error, coefficient of variation, and so on. And so this highlights that in preparing these formal privacy systems, there are a lot of different stakeholders. All of these different stakeholders have different things that they want to use the data for. And what ends up being accuracy for one may not be accuracy for another. And so the question is there a more systematic way that we could think about addressing these sorts of issues? In the interest of time, I'm going to skip past this application of thinking about the policy decision, but I'll come back to this in a different way towards the end. There are a few options that the Census Bureau has, or that in general you might imagine having, to solve these sorts of problems. So one would be to just sort of make bespoke publications that are tailored for each specific application. So we know that there's a specific application, say publishing data for the Voting Rights Act, that might require one model that delivers accuracy in one concept of accuracy, and that's different. And so we could return to the data multiple times, right, as long as we stay within the privacy budget, and publish data using different mechanisms. Another possibility is to reserve part of the privacy budget to get improved inference on particular questions, right? So this is kind of the concept of special tabulations, which again, we might use if we wanted to get improved classifications for a particular problem. And I suspect something like this will be part of the system anyway. And the third option that I want to focus on for the rest of my time is that we could use mechanisms that are broadly optimal for a wide range of uses. And so this brings in the idea of universally optimal privacy mechanisms. So the basic setting is we have, again, I'm going to think about this in the context where we have a single counting query. So we have a data set and we want to, say, count the number of entities in the data set that satisfy some criteria, like individuals who are unemployed. And then we have different data users, I, who all have potentially different preferences. So then their preferences depend on some choice variable, so some action that they're going to take, AI, and the true value of the counting query, or the true state of the world. So given the published output that comes from the mechanism, data users, right, these individuals are going to make choices based on their expected utility, where their expectations are over posterior beliefs about the true state of the world, the true statistic Q of D, given the output that they saw that was published, what came out of the privacy protection mechanism, M of D. And so in this setting, we're imagining data users that are engaged in a privacy-aware analysis. And I think this is an important point to think about in thinking about publishing data using formal privacy, is that if we imagine that data users are using the data naively, treating them as though they are not being subject to distortion, then it makes the analysis more complicated, although probably more realistic. So in a 2012 paper, Ghosh-Rothgarten and Sundarajan introduced something called the geometric mechanism, which is just like the Laplace mechanism, except for instead of adding Laplace noise to the count of interest Q of D, we instead add geometrically distributed noise that's scaled to the privacy loss epsilon. So geometric mechanism is provably epsilon differentially private, but even more interestingly, it's provably universally optimal for a particular class of information consumers. So what it means for it to be universally optimal is that if data users have access to the output from this mechanism, they couldn't do better by going back to the data custodian and asking for a data publication that was tailored to their specific use case. And this is not only sort of theoretically interesting, the way this works is the geometric mechanism, as it turns out, is able to publish count data in a way that make the privacy, the constraint that the publication be differentially private makes that constraint tight. So you're getting as much information out of the publication as you possibly could. So good news is that the geometric mechanism is approximated by the Laplace distribution, which, as we've seen, is in regular use, and we'll see in the second talk. But it's also easy to sample from and discrete, so it works well with these kind of count data. Bad news is that this universal optimality result requires that the actions have the same finite domain as the outputs. And the payoffs are maximized when the action matches the true count, and loss is symmetric when the action matches the count. So it corresponds to things that we think of like quadratic loss would be an example of a use case here. But this universal optimality result doesn't apply to other types of decision problems like the Voting Rights Act application that I didn't go over, but essentially any type of classification problem where you want to make a classification or a decision that changes sort of discretely when you pass some threshold, and others like it. So to put a little, to explain exactly what kind of problem, so simplified Voting Rights Act application, a policymaker has preferences where the count that they're interested in is, say, the count speaking Russian who have limited English, because we think that we might have to compel a jurisdiction to provide voting materials in Russian. And so in this simplified example, the action is just in the space 0, 1. This is the Voting Rights Act classification. And the ideal case is that the action that's chosen is exactly equal to the action that the assignment mechanism would choose if you knew the true data. So there's more good news and some more bad news with regards to this. So in a paper that I've been working on with my University of Georgia colleague, Nathan Yoder, we've been thinking about the data publication problem as a constrained information design problem. So in this setting, we think about the data custodian as trying to design informative signals on the basis of the data that they have, but they're operating under a constraint, under a differential privacy constraint. And it turns out that in that setting, the geometric mechanism is optimal in any case as long as the decision problem is monotone. So that is, in any setting where you want to choose a higher action when your beliefs put more weight on a higher count. So this would include classification problems like the Voting Rights Act. And it means that if that was the policy problem that you were trying to solve, then the decision maker, again, as long as they can conduct a privacy-aware analysis, would actually not do any better by asking census to provide a classification directly. They could just do the analysis based on the counts published with geometric noise and obtain equally accurate classifications. The bad news is that the geometric mechanism doesn't work for non-monotone decision problems. So non-monotone problems are ones where you want to take a particular action if this count is low or if it's high, and do something different kind of in between. So an example you might think of is if I'm trying to decide if I'm OSHA trying to decide how to allocate inspectors, if the number of accidents, say in a firm, is very high, I might suspect negligence and send inspectors there. If the number of accidents is very low, I might suspect fraud and send inspectors to investigate that. But kind of if the number of accidents sort of matches my expectations, then I might not target inspection activity there as much as I would to these other two cases. And then you can also think about SARS, COVID-19 antibody tests. So if I'm teaching my class in the fall, if I knew that if I had access to accurate antibody counts, which would be really cool. If the positive count was very high, I might not be too worried because I know there's a high degree of immunity. So, well, science is evolving. But I might not require masks. If the positive count is very low, then I think that the spread is under control, and so I won't worry about masks. If I've got an intermediate count, then I might kind of maximize my precautionary behavior. So takeaways, for counting queries, publishing with geometric noise could be optimal for a wide range of monotone use cases, but it does require that we assume that the users are going to be engaged in some privacy-aware analysis. If the users end up treating the data as though they were undistorted, then we have problems. There's more bad news in that there's no universally optimal methods for many non-counting queries. There's a series of impossibility results in a paper by Brenner and Nassim in 2014 essentially show in cases where you're either considering decisions based on multiple counting queries or other types of queries that it's no longer possible to develop universally optimal methods. Just to close out, other types of decisions that economists will be interested in are, of course, statistical decisions with differentially private population statistics. And I'm not going to say too much here. Dan, in his next talk, I think is going to talk about privacy-aware hypothesis testing. And he's got a couple of papers there. And the literature seems to be evolving and thinking about when and how we can test hypotheses when we have access to data that have already been distorted by differential privacy. In another setting of interactive data analysis, which Danny Goroff talked about in his opening comments, is a setting where you get to choose questions to ask a differentially private filter. And then when you see the results of your queries, go back and ask them more. So there's some good news here. And that is that, as he articulated, differential privacy seems to be able to help in preventing overfitting or generalization bias. And what's exciting about that is that, you know, even if multiple research teams had access to the same query system, it would sort of present generalization bias across the ensemble of analyses, even across different teams. There's some bad news, and that is that there's a very recent paper by Komarova and Nikopelov showing that point identification for certain estimators that we tend to be very interested in, like regression discontinuity designs, might be impossible. And so this is an area where there's a active research agenda, and I think growing need for more analyses on these topics.